Right, in the second part of this chapter, we are going to consider 16-bit timers. So in the first part, we mentioned the 8-bit timers, that we are using 8-bit registers, which is timer 0 and timer 2, or timer counter 0 and timer counter 2. And in this section, we are going to consider the 16-bit timers, which have got lots of capabilities. So 16-bit timers, they have got 16-bit registers, and it increases the range and the accuracy. So we have got 16-bit TCNT register, OCR, and ICR registers, which are all 16-bit. And also we have got TCCR, which we have got 3 different registers, A, B, and C, and we have got OCR, A, B, and C. And for each of these OCR registers, we have got individual OCF output compare flags for each of these. And we have got 1 input capture unit with noise canceller and edge detector, and CTC still available, and 10 independent interrupt sources, which we are going to discuss in the next chapter. And we also have rich PWM features, which we are going to discuss that in another chapter as well. So if we get into the details of timer counter 1 and 3, and you can see that we have got a 16-bit registers, but as AVR is an 8-bit microcontroller, we have to address this 16-bit register as TCNT H and TCNT L, for example. So the high byte and the low byte, like we were doing with the previous chapters. So for each of these registers that we already mentioned, with OCR, TCNT, TCCR, they have got these high bytes and the low bytes that we need to fill it out. So, and we also have the timer interrupt flags, which are related with the timer counter 1 or timer counter 3, or we can have an extended interrupt flags as well, which are in extended TIFR register. And if we want to play these around, we are going to see how are we going to use this with a 16 bits. So the first thing that we need to take care, as AVR is an 8-bit microcontroller, it can manipulate the data 8 bits at a time. And we can see that the all 16-bit registers in timer 1 and 3 requires 2 read and write operations through the 8-bit data bus. So in 16-bit timers, we should read or write the entire content of a register at once. So this is really important, otherwise we might have problems. So what does that mean? For example, we have got, I'll use the board. We have got TCNT1 registers contains 0 hex 15 FF. So what we normally do, we have to read the low byte of TCNT1. So TCNT1 low is going to be 0 hex FF. And then let's say we want to store it in R20. So that means R20 will have 0 hex FF value. And at the same time, the timer clock occurs. So that means the TCNT1 becomes 0 hex 600. So that is actually incremented when the clock occurs. Now, if you want to read TCNT1H, that is going to be 0 hex 16. And let's say we want to store it in R21, which is going to be 0 hex 16. Now, if we look at the value that we have read in R21, R20, that is going to be 0 hex 16 FF. So now, we believe that TCNT1 contains this value. However, it actually contains 0 hex 15 FF. So this is really a problem, and this problem exists in many 8-bit microcontrollers. But thanks to AVR designers, they overcome this issue or a problem with an 8-bit register. So this 8-bit register is called temp. So we use this temp as a buffer. So what is actually happening over there? Temp register is shared across all 16-bit registers in a 16-bit timer. So a direct read or write operation from or to the low byte of a timer register triggers a transfer between temp register at the high byte in the same clock cycle. So this is the definition over here. Now, this prevents the timing mismatches between the low and the high bytes. So how is that going to work? So let's give an example over here with the architecture that we have in mind. Let's say LDI R16 is 0 hex 15. Then out TCNT1H is R16. So what is actually we are saying over there? We are saying that store 0 hex 15 in temp of timer 1. So that's our first instruction. Then what we can do LDI R16 0 hex FF and out TCNT1L, which is going to be R16. And over here we can say that TCNT1L is going to be R16, and at the same time TCNT1H is going to be temp. Now let's analyze this. So after the execution of out TCNT1H, so after that execution, the content of R16, which is hex 15, will be stored in the temp. Okay, so over here we can say that temp is equals 0 hex 15. Now when the second instruction out TCNT1L is executed, the contents of R16, which is hex FF, is going to be loaded into TCNT1L, and at once, this is important, TCNT1H will have the value of temp, which is equals 0 hex 15. Now, when we want to read TCNT1, that means we will have 0 hex 15 FF inside. So this is the case in AVR with the 16-bit timers. We have got the temp register over there, and by using these commands, first the high byte is stored in the temp register, then we have the second instruction for the low byte that will be loaded at the same time with the high byte. So the only thing that we need to be careful over here, according to the internal circuitry of the AVR, we should first write into the high byte, okay, of the 16-bit register, then write into the lower byte. Otherwise, program does not work properly. This is because when TCNT1 low byte is loaded, the content of temp will be loaded into TCNT1 high byte. But when TCNT1 L register is loaded, temp is actually containing improper data, which we call it the garbage data. So it's not going to be the valid values that we are looking for. So always this one comes first and then this one. So load out the high byte and then the low byte. Another important thing over here, when we want to read these registers, so when we read the low byte of 16-bit register, the content of the high byte will be copied to the temp register. So once again, if we consider it in R20 TCNT1L and in R20 TCNT1H. So on the first line, R20 is equals TCNT1L, and maybe let's do it this way because we need to have the comments. I'm just gonna rewrite it. So in R20 TCNT1L, so that's going to be R20 equals TCNT1L, and in this case temp will be equal TCNT1H. And then when we run the second instruction, or when we execute it, TCNT1H, it's going to be R21, which is going to be equals to temp. So we need to pay attention to the order of reading the high and low bytes of 16-bit registers. Again, otherwise we'll have errors in the result. So we read the low byte. which will be loaded into R20, and high byte will be loaded into temp. And when we specified where this high byte is going to be loaded, that will be loaded from the temp. Okay, and this is the case for TCNT registers. When we consider OCR registers, ABC, it doesn't matter, it does not involve using the temp register, as the diagram says, because AVR does not update the content of the register of OCR, because OCR is actually updated by the programmer or the user. We just specify the value that we want to compare, so it's not going to be changed until we have changed that value over there. So these are the two important things that we need to consider when we talk about 16-bit timers. And the timer 1 and 3 clock sources, like we had with the timer 0 and 2, we also have the no prescaling or the prescaled clocks. If you want to have a larger delays, we can slow it down. And we also have this external pin like we had with the timer 2, so we can use that external clock source on TN pin on the falling edge or on the rising edge. And you can see these from the pin specifications, P6, which is showing 331, which is T6, and T1, which is in PD6. So when you want to configure, we have to configure these bits of the ports. And also, as they are sharing the clock sources, we need to use multiplexers over there. So timer counter 1 clock source, 2, and the third one, and they are having the prescalers 8, 64, 256, and 124, and they are just using a multiplexer, so we can easily implement these in either of these timer counter modules. So with the 16-bit timer counter, we have a different modes over here with the control registers that we can configure it out. But as you can see, the first one, which is 000, is the normal mode, and the fourth one, which is 0100, is the CTC mode. The rest are PWM modules, which we are going to see those later on. So when you want to configure it for normal mode, this is what we need to use for VGM values, for TCCR A and TCCR B, and for CTC we just need to use 01000 over there. So that's what we need to configure in these two modes of operation. And the output compare unit, which is similar to the timer 0 output compare, when we have a 16-bit comparator compares continuously with the TCNT. So whatever we load into OCR, it is going to be compared with the TCNT. So whenever the TCNT reaches over there, output compare flag will be set, and it can cause an interrupt and so on, and we can generate waveforms based on that. So to generate the waveform, we can use the COM pins or the COM bits of the timer, and we can use as a normal port operation or toggling or clearing or setting of those bits to generate the waveform. And input capture unit is a functionality for timer 1 and 3, so we can actually capture an event when it occurs. So the value of TCNT is captured in input capture register. So for example, analog comparator can trigger TCNT1 but not TCNT3, and we can use this module over here, which we're going to see this in the details as well. So let's give some examples, at least we can understand what's going on with an example, or how are we going to use a 16-bit timer to configure these things up. And before we give that example, I just want to emphasize something like we have done with the timer 0 and timer 1 in the normal mode of timer 0 timer 2 in the normal mode operation. Like you do remember, we have got this timing. So over here in the normal mode we have got a 16-bit value in TCNT. Okay, so what is actually happening over a time? We start from 0 and we go up to FF and then down. So over this period TOV1 will be equal 1, and then we count up again. When we reach there, overflow, and again TOV flag, another one, and so on. So this is how we are using this in normal mode. When we consider CTC mode, in CTC mode we have got, of course, again the highest value is FFFF, but we have got OCR value. So OCR1A, let's say it's somewhere here, okay, and that's FF. So when we set this OCR value, we reach there, we go down, we reach there, we go down, we reach there, and we go down. So at this point we are actually setting the flag OCF1A to be 1. Okay, so rather than TOV flag, we are setting output compare flag for 1A to be 1, as we are using OCR 1A. So these are the two modes that we generally focus if we are not using PWM modules and so on, normal mode or CTC mode. So let's see our first example now. Assuming Xtol 10 MHz, use timer 1 to write the program that toggles PB5 once per millisecond using normal mode. Okay, so before we write any code, we have to do some calculations, of course. And let's do those calculations first. So we have got F clock as 10 MHz. So 10 MHz, it's actually giving us 1/10 mega, which is 0.1 microsecond. So as we want to toggle it once per millisecond, what we need to do to calculate the number of machine cycles, this is going to be 1 millisecond divided by 0.1 microsecond. So that is going to be equal to 10,000. So we got that value now. Now, to load the TCNT1 in normal mode, as it says over here, we need to, as this is a 16-bit register, we have got 65,536 minus the value that we have, which is 10,000 for the number of machine cycles. So this is going to give us 55,536. So we can use this value for TCNT1, and we can start counting from that on. Now this can be either written in decimal or you can convert it to hex, which you are going to get D8F0. So this is going to be our TCNT1H, and that's going to be TCNT1L. And we can use it like this. Now let's write the code for it and let's see how are we going to configure it. So what we need to do first, let's write it as a subroutine again. So first we have to do some stack initialization, as we are going to create a subroutine. So let's start with init stack, and let's just give some tabs. LDI R16 0 hex 20, because we want the pin B5 to be toggling. That means SPI DDRB 5, so PB5 as an output. Then what we do, we clear the output, so LDI R17 0, so out port B R17, so PB5 is equals 0. Then, as we want to call this as a subroutine, we just need to say rcall delay, and we will call that subroutine. And once we get out from the subroutine, we have to toggle it, so R17 R16, this will perform the toggle D5 of R17, and of course we just need to do out port B R17. Then that will toggle, let's write that down as well, PB5. So once we are done, we can go back and start again, and we have to call the function again. Okay, so we initialize the port that we want to toggle, then we call the delay, and we just set to toggle it after a delay. So then let's give some break over here. We can call the subroutine delay and LDI R20. So we want to load TCNT1 high and TCNT1 low. So TCNT1 high, it's going to be 0 hex D8. So out TCNT1 high is going to be R20. Then LDI R20, the low byte is F0, so 0 hex F0 will be loaded, and then out TCNT1L, and that's going to be R20. So now we have got the values. So let's write comments over here just to make it clear. TCNT1H is going to be 0 hex D8, and TCNT1L will be 0 hex F0. So now we need to configure the TCCR 1A and TCCR 1B registers. As this is going to be in normal mode, we just need to set it, the TCCR 1A, to be 0. So R20, it's going to be 0 hex 00, and out TCCR 1A is R20. So VGM 11210, it's going to be 00, which is the normal mode of operations. Then we do the same thing for TCCR 1B, and we just need to set it to 0 hex 01. You can check this from the data sheet or from the lecture notes that is going to be 001. So TCCR 1B, it's going to be R20. And over here, VGM 132 VGM 12 is going to be 00. So normal mode. Now we have got the setup for the timers. What we need to do, we have to wait for the timer interrupt flag. So we have to check that. So over here we can just get the TIFR into R20, and then based on that we can say SPRS, which is skip next instruction, if R20 is set. So we have to check the timer overflow 1 flag. So if TOV is 1, skip next. Then what we can do, we have to wait over here and look for the flag. So that means that can be again. And then once we have got it, we'll skip the R jump and we'll do LDI R20 0 hex 00 and the out. So we have to stop the timer, TCCRB 1B R20 then LDI R20 0 hex 04. We have to clear the flag as well. So out TIFR R20 clear 2OV1 flag. And then we have to get out from the delay subroutine. We just say return. So what we have done, we have seen that we can set the TCNT1H and TCNT1L values, which we already calculated. So D8 F0. Then we can set the control register, so it's going to be a normal mode, no pre-scaling or nothing. And then we check for the TO1 flag, the overflow flag. If it's not set, we have to keep checking. If it is set, we skip the jump instruction and we stop the timer, we clear the flag, and when we return back, we perform the toggling over there. So this is how we can implement the delay using timer 1. So if you want to calculate the cycle for that square wave or the frequency of that square wave, what we can actually do, if I go back over here, so 10,000 machine cycles when we multiply with 0.1 microsecond, it will actually give us 1000 microseconds. So this is actually 1 millisecond pulse. So that means this pulse is 1 millisecond, this pulse is 1 millisecond. So in total we have got 2 millisecond period. So that means the frequency will be 1/2 millisecond, and that is going to be 500 hertz in this case. So that's how we can deal with the delay over here. Now the next thing that we need to consider, or we can mention one more thing. So rather than writing the hex values that we have calculated, we can also do minus 10,000 over here, the high and the lows. So the assembler can deal with converting it from the decimals to the hex values. So we can just use that minus 10,000 and that will do the job for us. Okay, or if you want, you can just write complete equation of it, and that's also valid for it. So you can use that both conditions. It's acceptable. And the next thing that we are going to consider, so we have the same program, but now we are in the CTC mode. So when we consider the CTC mode, we are actually saying that, okay, we are not going to wait for the overflow flag, but we are going to wait for the output compare flag, OCF. So I'm not going to rewrite the program again. I'm just going to show you the difference over here. If you look at it, this part is almost similar, but it's calling the delay function over here and toggling in a different manner. Now the thing is, as this was 10,000, with the CTC mode, OCR has to start from 0 and goes up to 9.9999, so 9,999. So to set this up, we just need to change OCR1AH and OCR1L values. So we have to set these. So either you can convert it to hex, which is 270F, or you can just directly use this decimal value over here, and you can just say the high and the low over here, and the assembler will automatically calculate the hex that it needs to count up. So another important thing that we need to consider over here, the TCCR1A and TCCR1B registers. So the 1A, it has to be 00 again, but 1B has to be configured in a way that it's in the CTC mode, which is mode 4 on that VGMs, and no prescaler. So the rest is exactly the same. We just need to monitor output compare flag 1A, and whenever we have got the flag set, we just perform the clearing the flag and stopping the timer and going back and toggling the output. So the way they work, it's pretty similar, only the other one is using TCNT and incrementing until the overflow, but the CTC mode is comparing with the OCR1AH register and OCR1AL, and that's the only difference. So this is another example. Assuming that clock pulses are fed into pin T1, write a program for counter 1 in CTC mode to make port C0 high every 100 pulses. Okay, so what do we need to do over there when we consider this? So when you want to count for an event, that means we are using the counter rather than the timer, we can look into this CSN2, CSN1 and CSN0 bits on the timer counter registers. So this is going to be an external clock, so it's going to be an external event, and if we are going to use the falling edge, we have to configure it as 110. If we are going to use it for a rising edge, we have to configure it as 111. So that's the only difference that we need to do. And as we are going to use 100 pulses, which is given to us with CTC mode, this is actually going to be 99. So another way of saying this, with this TCCR1B register, as the first bits are going to be 0, 0, 0, so 7, 6, 5, and 4 is going to be 0. Then VGM 1, 2, which is the third bit, it's going to be 1, and 2, 1, 0, it's going to be, let's use the falling edge, so 1, 1, 0 has to be configured. So this is 0 and this is E. So that's what we need to set for TCCR1B as 0 hex 0E for this configuration for external events. And when that is set, we just need to set, as it says, 100 pulses. OCR1AH is going to be 0, and OCR1AL, it's going to be 99. So we have to count from 0 to 99. And by using these two values, we can easily write a program for it. So the simplest way of writing this, let's say, as we are expecting to be the input for CTC mode pulse port C, but as we are capturing an event, we have to capture an event on this pin T1, which is PD6. So for T1, we have to set this PD6 to be an input port. So that means CBI DDRD6. So we can make T1 PD6 input. So we have to capture an event from there, or count an event from that pin. Then we can use SPI DDRC for outputting those into the port C0, and we can say that PC0 as an output. And then what we do, we have to set the control registers. So LDI R20 0 hex 0 out TCCR1A R20, and we repeat the same thing for TCCR1B. So over here, as we already calculated as 0E for the control register for capturing or counting an external event, this is going to be 0E, and out TCCR1B R20. So we can say that this is CTC counter falling edge. If you want to have a rising edge, we just need to change that to 111. That's the only difference over there. Now, what we need to do, we have to set the output compare value. So over here we say LDI R20 0, then out OCR1 AH to be R20. So temp, which we already mentioned, an 8-bit register is going to be 0. Then LDI R20, it's going to be 0 to 99 that we want to count, and out OCR1AL, and that will be R20. And if you write a comment, OCR1L is going to be R20, and OCR1H, it's going to be the temp. So those are set, and then what we do, we just need to go through and check if the flag is set in TIFR. So we have to read the TIFR, and SBRS R20 OCF1A. So we have to check the output compare flag if it's set or not. If yes, if no, R jump L1. So that L1 has to be somewhere here, because that's what we want to check. And let's just give a tab for these. So once we have done that, we just need to keep doing this until we get it, and when it's set, we can just clear the flag. LDI R20, the bit of OCF 1A. So clear OCF1A flag, and out TIFR R20. And then what we do, SPI port C0. So PC0 is equals 1, and CBI port C0, then PC0 is equals 0, and then we can just repeat this forever. So again, it has to be somewhere that we can set the OCR value. So over here we can just use again, and we can just repeat these continuously. So this is how we can count on an event and using the T1 pin, and we can just set an output based on that. And the last thing that we can say about these 16-bit timers, so in addition to generating PWM signals individually, timers 1 and 2 can be ganged to implement on chip modulator to generate waveforms modulated with carrier frequency. So we can combine these two together, and using OC1C pins or OC2 or PB7, we can send out a waveform which are modulated. So that's the end of this chapter 9, AVR timers and counters. If you have any questions, please note them down and you can ask me during the QA session. Thank you.